Okay, in the last class we had started discussing the FIR filters for implementation in digital systems, and then we had shifted our discussion to what do the zeros of the FIR filters tell us about the frequency response in general. We looked at an intuitive understanding of what the zeros do. Basically, if you place a zero, then what happens is whatever is the difference vector between the starting from the 0 to the unit circle, the length of that vector basically determines what is the magnitude of your frequency going to be at that particular frequency. And we also talked about the fact that FIR filters only have zeros. They don't have any poles except at z equal to 0 or z equal to infinity. And the last thing we noted was, since we want to focus only on causal FIR filters, so that means that we are not going to consider z equal to infinity poles. So we'll now move on from that general understanding to specific cases of FIR filters, and we'll look at three very basic types of FIR filters that arise in our design. So three basic types of FIR filters. And these are just examples to help you understand the discussion we had been having with respect to the zeros and FIR filters. So the first type, which we have studied very often, is a low pass FIR filter with a cutoff frequency of omega equal to omega c radians. So if you look at an FIR filter which has a cutoff frequency of omega c radians, first of all, if the length of the filter is capital N, then this FIR filter is going to have how many zeros? We'll have n minus 1, or we are often going to call it capital M zeros. And the reason for that is simple, that a length n FIR filter will give you a z transform, which is going to be a polynomial whose degree will be n minus 1. And if you have a polynomial of degree n minus 1, then it has, by the fundamental theorem of algebra, it has n minus 1 roots. And the roots of that polynomial are precisely the zeros. So if the length of the filter is n, then you have n minus 1 zeros. That is true in every case. Now, where will those zeros be placed as a general principle if you have a low-pass FIR filter? So I'll take the example that omega c right now is some number between pi by 2. So this is your omega c, and this is minus omega c. So the zeros of this FIR filter, since we know that the zeros are going to pull down the response of your FIR filter, most of the zeros of your FIR filter, you will see them being on the unit circle in the region outside the minus omega c to omega c region. So if I take the example of, for example, m equal to 3 or n equal to 4, length 4 filter, then I will have, and I take the case of a moving average filter, I will have a 0 here, here, and for example here. Right? You can, to make it a more stronger FIR filter, you can keep on adding zeros on the unit circle in the region away from omega c to minus omega c. Okay. So that is what a general FIR filter, which is a low pass filter, will look like in the Z domain. An FIR filter can have zeros in this region of the low pass filter, but they would never be on the unit circle. They will be a little bit away from the unit circle, and the goal of those zeros will be to make sure that your response doesn't overshoot. So you have a gain, your filter has a gain, right? And you want to make sure that your response doesn't overshoot too much. So you can have zeros, but they would never be placed on the unit circle in this low pass region, which you don't want to kill. But in the region where you want to kill, you would want to place the zeros on the unit circle precisely. So in MATLAB, there is a filter design tool called FDA tool, and we won't fully learn its functionality right now. I just want to use this tool to see the placement of zeros and how does that affect the response of my filter. So I'm going to launch this, and I'll be making some changes which may not fully register with you right now, so you can ignore that for the time being. The key idea is that here I can ask, the MATLAB is asking what is value of capital M, the order, which is sort of the degree of the polynomial you are working with, or how many zeros you are going to have. So I'll just say it is 4. MATLAB actually can design your filter in both continuous time and discrete time. I'm right now going to focus on discrete time. Let's say we want, so it's normalized, it's instead of minus pi to pi, it makes the frequency response symmetric. So it's only asking for a cutoff between 0 to pi, and it's just asking for the multiple that goes with pi. So when I say omega c equal to 0.25, that is effectively 0.25 pi, okay? And then I just do the design filter. This is what the filter looks like, but what I want to look at is actually the pole zero plot, okay? So I have 4 zeros, okay? And as you can see, that 1 0, so this is only showing you the 0 to pi region. There is a symmetric version of it from minus pi to 0, which is going to be exactly the same. Each of the dips that you are seeing, this is in dB. And each of the dips corresponds to a 0 magnitude, which is effectively minus infinity dB. So you're not going to see that. You're not going to see that fully. So what you are seeing instead is a dip, and that the location of that dip corresponds to the location of your 0. So you have about 0.46, which corresponds to this 0, which is at 0.46 pi, okay? Very near to pi by 2. So pi by 2 is 0.5 pi. And then you have another dip, which is due to this 0, okay? And you have the same thing happening. So you see that when I have 4 zeros, the only thing you can do with an FIR filter, and 4 zeros means it's a length 5 filter, right? This length 5 filter is able to give you this kind of a magnitude response, and you have to place them on the unit circle because you're trying to make the frequencies which are away from your cutoff go down, okay? So MATLAB lets me actually edit these zeros, and let's see if we can play around with what happens. So I am now moving this 0, and you see how the figure is changing. I am moving this closer to the smaller version, and the dip is now moving closer and closer, okay? If I keep on moving this, and the reason when I move 1 0, the other 0 is also moving because it's conjugate symmetric, and because we want to make sure that whatever is happening between 0 and pi is also happening between minus pi and 0. If you look at this, there is a conjugate button here. If I actually turn this off, then I can move one at a time, but then my frequency response is not going to be symmetric, and which means that my impulse response is going to be complex valued. Okay, so mostly we work with only impulse responses which are real valued, and our zeros are always then conjugate symmetric. So you move this and you see that the first dip is moving. Right? I move this around, and now if I move this other one, you will see that my other dip is moving. Right? Which is basically just telling us where the frequencies are, where my zero is, corresponding to that, this keeps on moving. Right? And if I just change it too much, basically the cumulative effect, you can see that, how that will play out. I would like to do the same exercise, but now with a significantly larger number of zeros. So let's say I'm now going to work with 64 zeros. So I have a lot more control. I have 64 zeros. It's a length 65 filter. I'm going to do this. This is what it looks like. You see that now, because I have more zeros, I really have a sharp cutoff from the low pass, which I want to keep, to the frequency that I told you to cut off. All the dips that you see are precisely going to be, again, what is going to be there. If you look at in the unit circle, you will see zeros there. Okay, so let's go to the pole zero plot, and this is indeed what you see. You have now 64 zeros, and most of them are meant to basically really drive down the response outside the 0.2 pi and minus 0.2 pi region. So this is what you get. Now, there are some zeros in the main region of 0.2 pi to minus 0.2 pi, but they are not on the unit circle. Okay? Their goal is to make sure that your response in the pass band region, in the low pass region that you want to keep, doesn't go above 0 dB. So they are there effectively to keep the response pulled near 0 dB. Okay, so let's play with this a little bit again. I'll just pick this zero, this group of zeros, and you see what is the effect of this zero as I'm moving it away, right? This zero is, because I moved it away, this is making my response in the low pass go higher. So this is sort of like taming the response in the low pass region. The purpose of these zeros is that. Okay? If I move the next one, you see it's going up. I move this region, so now my low pass gain has increased. So these zeros which are in the minus 0.2 pi to 0.2 pi region, they are sort of really clamping down the gain of my filter. But you don't want them to be placed on the unit circle, because if you place them on the unit circle, you are not going to make a low pass filter. Okay. So in general, you can make your low pass filter using these kinds of tools. But if you are really interested in like fancy filters that do things which are very special, you can't really name it. It's not low pass, it's not high pass. It's a filter that you want to design in a very specific way. All you have to do is just play around with these zeros, right? And you will find a response that meets your demand. So let's now move on to the case of then high pass filter, which is another type of filter that you often encounter with omega equal to omega c radians cut off. So we'll again assume that the filter has length n, which means that it has m equal to n minus 1 zeros. Okay, so the question is, we understand what do the zeros in the low pass filter look like. What should the zeros in the high pass filter look like? And the answer should be very simple. It is just a 180 degrees reversal of whatever is the low pass filter doing. So low pass filter puts zeros outside the minus omega c to omega c region because that's where it wants to kill the frequencies. So it puts zeros on the unit circle in that region. In the high pass, you just want to reverse this. Right? What you want is that all the zeros are now put in the region of the low pass frequencies because you want to kill the low pass frequencies and keep the high pass frequencies. So an example will be, let's now assume that your omega c is between pi by 2 and pi. So this is your omega c. And of course, you have minus omega c because you want it symmetric. So just like the case of low pass, and I'll again take the example of m equal to 3, it is going to be exactly a mirror image of your low pass filter, but now the zeros will be placed, for example, here. You can place the zeros here, and what that does is it makes sure that all the frequencies up to omega c, from 0 to omega c, are pulled down, but frequencies from omega c to pi are not pulled down. So if we want to construct a high pass filter, we can actually construct a high pass filter by just starting with a low pass filter. So if we could simply, a high pass filter can be obtained from a low pass filter by simply flipping or shifting the zeros by pi radians. You just move all the zeros need to be shifted by pi and you get your high pass filter. So mathematically, you can say that if a low pass filter has a zero at zeta k equal to rk e to the j phi k, then what you want is that in the high pass, the filter the zero gets shifted by an amount pi, so your magnitude stays the same, but you now shift it by an amount pi. Okay. And a shift by pi is simply minus r e to the j pi k. So if your low pass z transform is given by this expression, you have k equal to 1 to m, you have m zeros, z minus ek, which means that your zeros are at ek. Then you can construct a high pass filter by simply replacing z by minus z, because your high pass filter is simply a shifting of the zeros by pi radians, which is just changing the sign of your zero, or which is effectively saying you replace z by minus z. So you get low pass of z at z equal to minus z. Okay. And you get p0 pi k from 1 to m minus Z minus EK. Okay. So that's the only difference between a low pass and a high pass filter. They look exactly the same. The zeros in the low pass filter get moved by 180 degrees by pi radians to give you a high pass filter. We have selected a high pass filter. The rest of the discussion for this tool we'll have later. Let's say we want 3 zeros and our cutoff is 0.8. We say design filter, and then we go to pole 0. This is where the zeros look like. Right? Previously, if you remember, the zeros were, I had a 0.2 cutoff, and the zeros were at this. So these zeros almost were here, but this 0 was at this other location. Right? So now I have just sort of moved their region. Now I have zeros in the low frequencies and no 0 in the high frequency. Now let's go back to the design and increase the order. Let's say I have 64 zeros. And now go to the pole 0. And again, we sort of see a mirror image of what we saw earlier. Now my low frequencies are all getting attenuated. So I have zeros on the unit circle around those frequencies. And then in the region that I don't have attenuation, I just have zeros sort of encapsulating that region so that my gain doesn't become too high. If once again I go to edit tool and I see that the effect of, for example, moving this 0 is my gain starts shifting up if I move it away from 0. If I move any of the zeros that were on the unit circle, if I move that, then what happens is I start seeing that dip, that region sort of start bumping up because I have moved it away from 0. If I move it this way, again that happens, but even this region is now starting to move up. So again, a simple principle: as you move zeros, it's going to affect different frequencies, and you can just see how far it is from certain frequencies to guess what would happen to your frequency response. You can use similar kind of ideas to talk about band pass filters, band stop filters. We won't go into the detail. I do want to bring up one other special type of filter which has a lot of applications. It's called a notch filter, and we are going to just talk about a very simple notch filter. You can make them more sophisticated. A notch filter is basically the idea that sometimes we are interested in killing off a single frequency. Okay. So for example, in many circuits, like let's say there is interference, you have a circuit which is very close to some sort of a power source which is generating this 50 hertz signal, and because of interference you get this 50 hertz interference in your signal, and you want to use your signal but you just want to kill that 50 hertz power signal. Okay, that's kind of an example of a notch filter. Or let's say you were recording my voice and behind this there was constantly some fan sound which is a constant frequency, right, which sort of creates a noise, a clicking or some other sound in the signal, and you just want to kill that one frequency. So all of those examples are what's called a notch filter. A notch filter looks like the following in the frequency domain. It has basically, you want it to be very stable everywhere except one location, and then you want it to be like this. Ideally, you want this region to be as small in width as possible, and that's where the notch filters get more sophisticated. But a very simple notch filter is really easy to implement given what we know about zeros. So you have a notch at omega naught and of course a notch at minus omega naught. So based upon what we know about zeros and their effect on frequency response, what is the natural thing that comes to our mind in terms of designing such a filter? What this says is you want two specific zeros, one at omega naught and one at minus omega naught. Effectively, the simplest notch filter is nothing more than a length 3 FIR filter. You just build a length 3 FIR filter where the location of the zero is the location of where you want the notch to be. And that's it. Now again, that won't be the perfect notch filter that you can work with, but that's a very simple and really easy to implement filter. So let's look at, it's so simple that you can even derive its expression. So if you want this kind of a notch filter, what this means is in the pole zero diagram, you want a zero at e to the j omega naught. So omega naught means you want a zero on the unit circle at omega equal to omega naught. And you want a zero at e to the minus j omega naught. And if you know the zeros, you should be able to figure out what is the z transform, and from that you can figure out what the coefficients are. So this means that a notch filter has a z transform. We have two zeros. How do we write the zeros? If we have two zeros, we write 1 minus e to the j omega naught z inverse. So that corresponds to this zero times 1 minus e to the minus j omega naught z inverse. That corresponds to this zero. That's my z transform. And now I can just simplify this z transform. I solve this, I get 1 minus e to the j omega naught z inverse minus e to the minus j omega naught z inverse plus z to the minus 2, because e to the j omega naught and e to the minus j omega naught is going to be 1. And now I just use the Euler's identity. I get 1 minus 2 z inverse e to the j omega naught plus e to the minus j omega naught over 2 z to the minus 2. Now this is simply cosine of omega naught. So I get 1 minus 2 cosine of omega naught z inverse plus z to the minus 2. So this is the z transform of my notch filter. And for FIR filter, if I am given the z transform, as we talked about earlier, the filter coefficients are nothing more than the coefficients of your z polynomial. So this means that whatever is this is my h0, this is my h1, and the coefficient of this is my h2. So a notch filter is basically a filter, if I write it in vector form, 1 minus 2 cosine of omega naught and 1. Okay. So this is the simplest form of a notch filter that you can have. The omega naught that you are interested in basically determines where your notch is going to be. You just change the second coefficient of your filter, and that's about it. Okay. So let's go to MATLAB and try to verify this. I have first 1, and then I have minus 2 times cosine of, let's say we are interested in a notch at 0.45 pi. And then have one more. Okay, so that is my filter, and if you remember your FV tool, I designed that, and this is what you get, right? Exactly, and again, this is 0 to pi. That's why you don't see the other region, because it's symmetric. So we get exactly a notch at 0.45 pi. And in this one too, I could just look at the pole zero plot, and indeed I have just two zeros, right? Of course, we did it that way. Our equation came from this picture. So that's the simplest, easiest notch filter that you can ever build. It's not perfect, because what you want is perhaps too sharp of a drop at the notch, right? But you can't get any simpler than that. Okay. So this is just design of special filters. You have low pass filter, high pass filter, maybe a band pass, band stop filter, a notch filter. In many cases, you would be interested in what I call specialized filters, which is that they don't really have a nice shape. They are sort of a random shape, random in the sense that it can take arbitrary shape. And you are interested in how do I implement that kind of a filter? Well, in that, the only way to do that for specialized ad hoc filters is there is no systematic manner. The only thing you can do is actually really, literally just play with zeros. You just move zeros around, okay? And people who are really, it's like an art that once you have enough insight, someone comes and says, I want this kind of a shape, you're automatically aware that, okay, if I place zeros around this region, this is what it will look like, and then you just wiggle around and you get the right shape. So if design of specialized or arbitrary shaped FIR filters can be best handled through trial and error of zero placement. Again, we are not talking about poles right now because FIR filters don't have any poles other than z equal to 0. Right? We'll come to that when we come to IIR filters. Now, so for arbitrary shapes, there is no other recipe that is available to us. What I have shown you is you can play with it and figure out. But if you are going after systematic designs of FIR filters, which at least you can get analytical expressions for their, for example, impulse response, even if they are infinite length, then we can talk about how do you systematically from that design FIR filters. So our focus will be on systematic design of FIR filters through, we'll look at what is called the windowing method. There are many other methods. If you go and look at, for example, FDA tool, it gives you a whole list. But we are only going to learn about the windowing method, which effectively just says that you start with a frequency response, you compute its inverse Fourier transform, and you get an infinite length filter. And then you systematically reduce it to a finite length filter. And that's how you build an FIR filter. So we will do that, but before that, we want to make sure we understand certain terms for FIR filters. So our first goal is understanding desired characteristics of FIR filters. So the next few minutes, or perhaps even going into the next lecture, we'll just be talking about abstract ideas. We'll try to motivate why those are the things that you should care about. So one of those characteristics we already know. So characteristics of FIR filters. So the first one we already know, that we are interested in only causal FIR filters. So what is a causal filter? This means that h of n equal to 0 for all n less than 0. And a causal filter we are interested in because that's only the realistic filter that we can work with. A causal filter means that the output only depends upon current or past input. It does not depend upon future input. Okay? So causality in filter design is a given. There is no more need to motivate why we need causal filters. Okay? So our filters will always start at hn at n equal to 0. Now, this other characteristic we have to really understand. They are called linear phase FIR filters. So in practice, we always want a filter, and that is regardless of whether we have FIR or IIR. We want a filter which has a linear phase, which we'll explain more. Now, designing a linear phase IIR filter that is causal is impossible. So that is why FIR filters are preferred so much, because you can design filters which are linear phase. So let's try to understand what is a linear phase FIR filter. A filter HN has a frequency response h of e to the j omega. Now I will write that in terms of magnitude and phase. So I have magnitude of that, h of e to the j omega, and I have phase of that, which I'll write it as e to the j theta omega, where theta omega is nothing but the argument of h of e to the j omega. So just the phase of this. Now, so far we have focused our discussion on only the magnitude. We have talked about, well, if the magnitude does this, then it is a low pass filter. If it does that way, then it's a high pass filter, and so forth. So what about the phase? Can we completely, what is the value of the phase? Well, the value of the phase is sometimes important, at other times it is not that important, and we'll try to motivate that. So while the magnitude information is one of the most important aspects of a filter, and this is true regardless of whether we are talking about FIR or IIR, we cannot simply ignore the phase information. In most of our discussion, phase is just a secondary thought. But in reality, phase is not something that you just say, if I only focus on magnitude, I'm good. No, you have to care about phase. Now, to understand what is the role of phase, let's look at the following case. So what does the phase teach us? Well, let's look at the case of a filter which has magnitude 1. It has nothing more but phase. And let's try to understand what is that filter doing. So let's look at a filter h of e to the j omega, which is given by e to the minus j omega n naught. This means that my theta omega is minus n naught omega. So what is this filter? This is a simple filter which is hn equal to delta of n minus n naught. Okay. If I input xn to this filter, then what is my yn? So what is the role of a filter which is simply a shifted impulse? So my yn, which is simply xn convolved with delta of n minus n naught, is simply x of n minus n naught. So this is the type of filter which does not really impact us that much. And what is the goal of this filter? It is just doing a delay. If you record some speech and you input it to this filter, what is that going to do? Let's say if the delay was 1,000 samples and you were recording 1,000 samples per second, it's going to just delay your output by 1 second. You're going to hear the same signal 1 second later. So a filter like this has very little impact other than delay on your output, and we say that this is a good filter in terms of its phase. Now, let's look at the phase of this filter. This phase is a linear function. This is a linear function of little omega. Okay? So what we say is that if you have a phase which is a linear function of little omega, then that filter does nothing more than simply delay your input by a certain amount of time. And delay never hurts anyone unless it's in centuries. Delay doesn't change the nature of what you are getting out. You hear it today or you hear it tomorrow, it's not going to sound any different. Okay? So a linear phase and the term linear phase simply means what is being multiplied with e to the j. Right? So a linear phase, in this case, it is minus omega n naught. It's a linear function of omega with a slope minus n naught. Simply means that the entire signal is delayed by n naught samples. Now, linear phase is a good thing since all frequencies are delayed by the same amount. Let's again focus on the case of voice. Right? Our voice is not simply made up of frequencies. Like if you take the DFT of my voice and you see that I generate these frequencies, And if you generate any other signal with those frequencies, you are not going to regenerate my voice. Why is that? Because it is not simply the frequencies that are present in my voice, but also their temporal relationship with each other. Whether a low frequency is generated first and a high frequency is generated later, and so forth. Okay? So frequency itself does not give you the timing information. And a linear phase, what it does is it delays all the frequencies by the same amount. So you hear everything as it was initially. And what that does is you have no change in perception at the end. Now, in order to see how good, so this is just an example of a filter which had just a phase, and that was linear phase. So you can generalize it and you can say that I have a filter h of e to the j omega, which has this magnitude and this phase term. And people try to figure out how close this filter is to having a linear phase. If you have perfect linear phase, then that's great, because that means that the frequencies, the order in time in which they were entered is the order in time that they will exit, maybe with certain delay, and there will be no change in perception. If you build a low pass filter, for example, with the same magnitude, but actually your phase is not linear, what you will hear at the end will sound different than the case when you had a linear phase. The reason for that is that some frequencies are being delayed more and some frequencies are being delayed less. So the relative position of frequencies in time changes and your output perception changes. So the way you measure whether a filter is close to being a linear phase is through what is known as group delay. Group delay basically takes the derivative of, it's written as tau g of little omega, and what you do is you take the derivative of your phase with respect to little omega. And if this group delay ends up being a constant, then that means that your system has a linear phase. If it ends up being very near to constant, then it has a linear phase. Okay, so if I take the previous example, we had theta omega was equal to minus omega n naught. This means that my group delay is equal to n naught, which means that all of my frequencies are delayed by the same n naught. Their relative position in time is not changed. Okay, so that is a good kind of a filter whose group delay is a constant, or in other words, whose phase is a linear function of omega. You would see, for example, cases, especially in IIR filters, you will actually see that you get group delays which are not constant. And that's why those kinds of filters are not preferred, at least in certain applications. So if I had, for example, my phase was like this, then my group delay is going to be 2 omega. So this is now not a constant. This means that my higher frequencies are being delayed more and my lower frequencies are being delayed less. My relative position of my frequencies will change and your output perception might change. In this example, what we see is that higher frequencies are being delayed more, and what this means is that output frequencies or the output signal will have the same frequencies as the case of right? Because you haven't changed the magnitude, you are not going to change the frequencies that are going to be present in your output signal. But they will be changed in position temporally. So what time a frequency appears in time and what time another frequency appears, that could shift. And for signals where this information is really critical, like voice, what you could hear at the output could be completely different from what you intended. So this can cause the output signal to be different in nature. So in general, for many applications, our goal is that we want to design filters which have linear phase. So try to seek filters with linear phase, which means that our filter response should be along the lines of it has magnitude, and then its phase is e to the minus j omega, some capital D, some number. And in that kind of a filter, you can completely ignore the phase information. And FIR filters with linear phase are relatively easy to make. If we obey certain properties, we can do that, but IIR filters, which are causal, cannot be made linear phase. And so that's the trade-off that you face when you are designing filters. In general, IIR filters are rather simpler in terms of their construction. You will require much less hardware to implement an IIR filter with the same cutoff frequency, for example, than an FIR filter. But what you end up with is a filter which does not have linear phase. And so if your application doesn't permit a nonlinear phase, then you should stick with an FIR filter. So I just want to go back to the FDA tool, which also has a plot for the group delay that you can use to verify whether the filter has linear phase or not. The way I'm constructing the filter, it has a linear phase. This is what the impulse response of the filter looks like. And this is what is minus d phi over d omega. This is exactly the group delay that we defined. Okay, and the group delay of this is 5. And it's a constant, as you can see. And I could have looked at the phase response too. It's just wrapping. It is linear phase. The reason you see sort of this going up back and forth is because of the wrapping that goes on. So a group delay is much better thing to look at than the phase. Okay, this is the case where you have a constant group delay. It's a linear phase filter. You are all good. So we'll study later what does linear phase, how can you guarantee linear phase? There are types of filters. FIR filters, we'll call them, they have very sort of uninteresting names. We call them type 1, type 2, type 3, and type 4. So engineers can't apparently come up with fancy names. Right? But we'll study that later, but let's just take a look at this example. For example, let me move this 0 around, right? And because of what I'm doing, you see that the group delay, what I have above is the group delay, okay? And this is an example where I have changed the group delay of certain frequencies. Because if I don't simply just moving the zeros around, and if I don't pay attention to the constraints that force an FIR filter to be linear phase, then I can actually mess up the linear phase of the filter. So even though I started with a linear phase, what you see here is that for most frequencies it is still linear, it's a constant, but then I have these frequencies, they have now a negative delay, so they have sort of been advanced. Okay, it's negative, so negative 30 means that they have been advanced, they are now going to appear earlier in time. And it's important that when we sort of mess around with the zeros, we keep the idea in mind that we have to make sure our group delay stays constant, which means we stay with the linear phase. So if I keep on doing, you see that the effect is appearing, and at some point I'll get, now this, for example, is not, this is not perfectly linear phase, right? But the difference between samples, the highest group delay is 4 and the lowest group delay is 1.6. For certain applications, that group delay might be acceptable. But it all depends upon the application, and no one can tell you whether this is acceptable or not. Only the person who is implementing, who knows what kind of system they are working with, can do it. So I want to use this, I want to stop here with the understanding that you can't just move around your zeros and not worry about the phase. You can't just look at the magnitude response and say, this is doing what I want it to do. You have to look at the group delay too and make sure that you are getting close to the linear phase. Otherwise, you can be in trouble depending upon the application.